Welcome you all. On today's session, so I will explain how to solve the numericals on Francis turbine. So go through this first numerical, the problem number 1. The following data are given for a Francis turbine. Net head is 70 meter, speed is equal to 600 rpm, power at the shaft is 367.5 kilowatt, overall efficiency is 85%, hydraulic efficiency is 95%, flow ratio is equal to 0.25, width ratio is equal to 0.1, outer diameter to inner diameter ratio is 2, the thickness of vanes occupy 10% of the circumferential area of runner, velocity of flow is constant at inlet and outlet, and discharge is radial at outlet. Determine first one guide blade angle, second one runner vane angles, third one diameter of runner at inlet and outlet, and width of wheel at inlet. Now note down the given data here. So this numerical is related to Francis turbine. So net head H is given as 70 meter, speed N is equals to 600 rpm, power at the shaft P is equals to 367.5 kilowatt, overall efficiency neta O is equals to 85%, hydraulic efficiency neta H is equals to 95%. There's a flow ratio is equals to the xi value is given this ratio of Vf1 by square root of 2gh is 0.25. Width ratio is given. The width ratio is equals to ratio of B1 to the D1 is 0.1. Outer diameter to inner diameter ratio. The outer diameter is denoted as D1 and inner diameter is denoted by D2. That means the D1 to D2 ratio is 2. The thickness of vanes occupy 10% of circumferential area of runner. That means the area of contraction is 10%. So that is taken as C is equals to 100% minus 10% is equals to 90%. So that means the C value is equals to 0.9. The velocity of flow is constant at inlet and outlet. That means Vf1 is equals to Vf2. Discharge is radial at outlet. Discharge is radial at outlet. That means alpha 2 is equals to 90 degree. So then determine diameter of blade, guide blade angle alpha 1, runner vane angles beta 1 and beta 2, diameter of the runner D1 at inlet and D2 at outlet, width of the wheel at inlet is B1. So now this is given data. H is equals to 70 meter, N is equals to 600 rpm, power P is equals to 367.5 kilowatt, overall efficiency is equals to 0.85, hydraulic efficiency is equals to 0.95, area of contraction there is a 10% is given for that reason. The C value is equals to 0.9. So now flow ratio is equals to Vf1 by square root of 2gh is equals to 0.25. Then width ratio is given B1 to D1 is equals to 0.1. Then outer diameter D1 to inner diameter D2 ratio is 2. Now to find alpha 1 is how much? Beta 1 angle, beta 2 angle, diameter at inlet, diameter at outlet, width at inlet. So now flow ratio is equals to Vf1 by square root of 2gh. So that value is given as 0.25. So by that relations we can find the value of Vf1. So here the flow ratio is given 0.25. and 2 into square root of 2 into g value is equals to 9.81. Head is given as 70 meter. Here vf1 is unknown, that value is 9.26 meter per second. So now discharge formula is equals to q is equals to c into phi into d1 b1 into vf1. So here in this one pi, so pi d1 b1 represents this is the area of the flow. So pi d1 b1 represents area of the flow. So then vf1 is equals to velocity of flow. The velocity of flow. So now substitute here the in this one the q is unknown. The q is calculated by using the overall efficiency expression. The overall efficiency is equals to the ratio of power developed to power available at the inlet of the rotor. So that is rho g q h. The overall efficiency value is given. So that is 0.85 and power is equals to 367.5 kilowatt. The density of the water is 1000. G value is equals to 9.81. Q is unknown and head is H is equals to 70. So by the simplification of this expression, the Q value or discharge is calculated 0.627 meter cube per second. So now from the discharge expression, so now runner diameter at inlet and outlet is calculated by using this discharge expression. The discharge is equals to C into pi d1 b1 into vf1. So q value is known, c value is known, phi is a constant. So d1 is unknown. So once again b1, the width ratio is given. b1 by d1 is equals to 0.1. So that means now b1 the b1 is written in terms of what? d1, that is b1 is equals to 0.1 d1. The same thing is substituted here into vf1 value is known. So that means only one unknown in that case, that is what? The d1, the diameter of the wheel. So now diameter of the wheel is calculated as, so here instead of b1 it is taken as 0.d1 and Vf value is known and d1 is equals to 0.496 meter. So this is a velocity triangle for given conditions, the velocity triangle for Francis turbine. So this one is the inlet velocity triangle. So here it is, this is inlet velocity triangle, inlet velocity triangle. So this one is a outlet, it is outlet velocity triangle. So in outlet velocity triangle, the condition is given, the discharge is radial. The discharge is radial means alpha 2 is equals to 90 degree. So here this alpha 2 is equals to 90 degree. So for that reason, the Vf2 is equals to V2. With that radial discharge, the V2, the observed velocity exit is equals to flow velocity, that is Vf2, and the value of Vu2, the value of Vu2, that is the tangential velocity at the exit is equals to 0. The exit is 0. So this is a velocity triangle for that given conditions. So now the d2, the inner diameter is calculated by the ratio of d1 by d2 is equals to 2. So with respect to that ratio, the diameter at exit is equals to 0.245 meter. Next, width of the wheel at inlet. If you know the diameter of the runner at inlet, so then we can easily find the width of the wheel by using the width ratio. So that is b1 is equals to 0.1 d1. So now diameter is equals to 0.496. So with respect to that, the width of the wheels at inlet is equals to 0.0496 meter. Guide blade angles and hydraulic efficiency. So here, first of all, you have to find out the bucket velocity or blade velocity. So that is calculated by pi d1 n by 60. So u1 is equals to 15.39 meter per second. So now hydraulic efficiency is equals to VU1 into U1 by GH. So here the hydraulic efficiency is given, the VU1 is unknown and U1 value is known and G value is equals to 9.81, head is given as 70. With respect to that, the tangential velocity at inlet is equals to 42.38 meter per second. From outlet velocity triangle, the tan alpha 1 is equals to Vf1 by Vu1 from outlet velocity triangle, that is a inlet velocity triangle. From the inlet velocity triangle, there is a tan alpha 1 is equals to Vf1 by Vu1. So now we know the value of Vf1 as well as Vu1. That means now tan the alpha 1 value, that is the fixed blade angle, this alpha 1 is equals to 12.3 degree. The runner vane angle at inlet and outlet is calculated by using once again from the trigonometric relations by applying the trigonometric relations in that velocity triangles. The beta 1 is equals to Vf1 by Vu1 minus U1. So the Vf1 is equals to 9.26 and Vu1 is equals to 42.38 and U value is equals to 15.39. Hence the beta 1 angle is 18.93 degree. So from outlet velocity triangle, the U2 is equals to pi d2 n by 60. Now U2 value is equals to 7.6 meter per second. Tan beta 2 is equals to Vf2 by U2. So that is equals to the Vf2 is equals to 9.26 and U2 value is equals to 7.6. Hence the beta 2, the blade angle at outlet is equals to 50.62 degree. To move on to the second numerical on this Francis turbine. The external and internal diameter of an inward flow reaction turbine are 1.2 meter and 0.6 meter respectively. The head-on turbine is 22 meter and velocity of flow through the runner is constant and is equals to 2.5 meter per second. Guide blade angle is 10 degree and the runner vane angle, vanes are radial at inlet. If the discharge at outlet is radial, find the speed of the turbine, vane angle at outlet, hydraulic efficiency and also draw the velocity triangles. So this was the inward flow reaction turbine. That means inlet of the fluid is taking place at the outer circumference of the runner and exit will taking place at the inner radius of the runner. So that means D1, the external diameter is taken as a D1 and internal diameter is taken as a D2. And here D1 is equals to 1.2 meter and D2 diameter at exit, the internal is equals to 0.6 meter. The head on the turbine is 22 meter, H is equals to 22 meter. Velocity of flow through the turbine is constant, that is Vf1 is equals to Vf2 is equals to 2.5 meter per second. Guide blade angle is 10 degree, that is alpha 1 is equals to 10 degree. Runner vanes are radial at inlet. Runner vanes are radial at inlet means beta 1 is equals to 90 degree. If discharge at outlet is radial, that is at exit, now alpha 2 is equals to 90 degree. So now find what is the speed of the turbine N, vane angle at outlet, that is a beta 2, hydraulic efficiency, then also draw the velocity triangles. Now write the given data here. H is 22 meter, beta 1 is 6 to 90 degree, beta 2 is unknown, you have to calculate. Hydraulic efficiency is also need to calculate. N we need to calculate, and alpha 1 is given as 10 degree and Vf1 is equals to Vf2 is equals to 2.5 meter per second. Diameter D1 is given as 1.2 meter, diameter D2 is equals to 0.6 meter. and this is a velocity triangle for that given conditions. So in inlet velocity triangle, so this one is inlet velocity triangle. In inlet velocity triangle, so here the blade angle at inlet is 90 degree. Correct, blade angle at inlet is 90 degree. That means beta 1 is equals to 90 degree. So with respect to that, the Vf1 is equals to Vr1. The relative velocity at inlet is equals to flow velocity at inlet, and the relations u1 is equals to vu1. u1 is equals to vu1. So this is a condition at inlet velocity triangle. And in exit velocity triangle, the discharge is radial. The discharge is radial. For that reason, alpha 2 is equals to 90 degree. Alpha 2 is equals to 90 degree. For that, v2 is equals to vf2. Absolute velocity at exit is equals to flow velocity at exit. And once again here vu2 is equals to 0. The tangential velocity at exit is equals to 0. So this is generalized velocity triangle for this given numerical. So from inlet velocity triangle, the alpha 1 is equals to Vf1 by u1. So the alpha angle is given as 10 degree, and Vf flow velocity is constant as 2.5 meter, and u1 is unknown, and u1 is equals to 14.18 meter per second. The speed of the turbine is calculated. u1 is equals to pi d1n by 60. The u1 is known, pi is constant. The diameter at inlet is 1.2 meter. The n is unknown. Then speed of the turbine runner at inlet is equals to 225.65 rpm. Vane angle at outlet, or beta 2 angle at outlet. In order to calculate that one, we require the u2 value. The u2 is calculated by the relations or the expression pi d2n by 60. u2 is equals to pi into the diameter at the inlet is equals to our exit is 0.6, and n is already calculated, there is 225.65, and u2 is equals to 7.089 meter per second. From outlet velocity triangle, the tan beta 2 is equals to Vr2 by u2. So Vr2 value is, that is a Vf2. The Vf2 by or there is a Vf2 value is 2.5 divided by 7.089, and beta 2 value is equals to 19.42. The hydraulic efficiency is calculated by using the expressions hydraulic efficiency eta h is equals to Vu1 into U1 by GH. So that is equals to U1 into U1, because Vu1 is equals to U1 at the inlet velocity triangle divided by GH. There is a 14.18 square by 9.81 into head is a 22 meter. So now hydraulic efficiency is 93.16%. So this is a method of solving the numericals on Francis turbine. Thank you.